Hey there, welcome back to HackCode. In this video, we're tackling a classic bit manipulation problem, number of 1 bits. This is also known as halving weight problem. It's a fundamental question that's not only popular in interviews but also great for understanding the bitwise operations. Let's dive in. So here, we have to write a function that takes the binary representation of a positive number and returns the number of set bits it has. And this is also known as halving weight, as we discussed. So here, what is set bits? A set bit refers to a bit in the binary representation of a number that has a value of 1. So here, for n is equal to 11, output is 3 because we have 3 bit sets in the binary representation. Similarly, for n is equal to 128, the output is 1 because we have only 1 bit set in its binary representation. Similarly, we have example 3 where we have the output is 30. So here the constants is n lies in the inclusive range of 1 and 2 to the power of 31 minus 1. So here the follow up is, if the function is called many times, how do you optimize it? So let's look into that. Approach 1 is loop and bit manipulation approach. So what is the logic here? The logic is to iterate over each of the 32 bits of the integer, and for each bit we check if it is 1 and then we increment the counter if it's true. So what are the steps? So first we initialize the counter variable to 0 and then we loop through each bit of an integer using a for loop or a while loop, and then in each iteration we use the AND operation with the 1 to check if the least significant bit is the 1. So and then we right shift the integer by 1 using the right shift operator to check the next bit in the next iteration. So after that we increment the counter if a 1 bit is found, and then we continue until all bits are checked. After that we return the count. So let's see what I meant. Here in approach 1 we do loop and shift. So here we take a typical example of 11 and explain the approach 1. So here the binary representation for 11 is 1011. So the first step is to check for the LSB and with n in 1. So basically this is the number we have 11, and then we do a bitwise operation and with 1. So here the LSB we get is 1. So now we add it to our count since we are interested only in the number of 1 bits or set bits. So here we right shift n by 1. So that means that for 1011 we just drop this thing, and then we doing left shift is nothing but like shifting all bits to the 1 and then dropping the rightmost bit, that is LSB, and then adding 0 to the leftmost bit, that is here. It's just we fill in the bits with 0 here. So here we repeat the same thing in step 2, and then we take this and do a AND with 1, and then LSB is 1 here, and then we do a right shift again here, so it becomes like this 0 0 1 0, and then we repeat the check. Here we get the LSB as 0 because 0 and 0 is 0, right? So we get 0, and then we do a right shift again by 1. So here what we are getting is 1, and then we repeat the check. We have the left LSB is 1, and then here we right shift by 1, so we get 0, and then here it's the ending condition because n becomes 0. The loop ends here. We have the count of 3. So here let's look into the code. As we discussed, we initialize the count with 0, and then while n exists, we just do loop through, and then we just increment in the count with n and 1. Basically, if it results in 0, we get 0. If it results in 1, we get 1, and the count is incremented. And then we right shifting it by 1. So and then we returning the count. So here the time complexity is O of 1. Why O of 1? Because the loop runs as a constant times 32 times for 32-bit integer, and the space complexity is O of 1, as we only use a variable to keep the count. So next is using bitwise trick. So here the logic. Use a trick to directly target the least significant 1 bit and then turn it off in each iteration. This reduces the number of iterations required. So here what are the steps? First we initialize a count variable to 0, and then we use a while loop to iterate as long as n is not 0. In each iteration, we subtract 1 from n and then perform an AND operation with original n. This will turn off the least significant 1 bit. And then we increment the count after each operation. Return the count when n becomes 0. So let's go over the approach. So here also we're taking 11 as an example and explain the approach 2. This approach is also known as Kernighan's algorithm. So this approach actually turns off the rightmost 1 bit in each iteration until the number becomes 0. So here the initial number we have is 11. This is the binary representation for 11. And so here the step 1 is to turn off the rightmost 1 bit. So what we're doing is n into n minus 1. So this is the representation of 11 and this is the representation of 10. and then we're getting the 1010 by doing an AND operation. So here we turn up the rightmost 1 bit and the count is 1. The step 2, we repeat the same process. We take this and then 1010 is here we have, and then we do with like 10 and 9. So and then we get 1000. So here under rightmost 1 bit is turned off and the count is incremented with another 1. So repeat the process. So n is equals to n into n minus 1, and then we have 8 into 7 here. So here what we're getting is 0, and then here the last 1 bit is turned off and we do count it, and now the n is 0. So the ending condition is n becomes 0 and the loop ends. So the count of ones is also 3. So as we see here, this approach reduces the number of steps. Previously we had how many steps here? Like we concluded at the 4th step, but here we concluded only 3rd step. So here let's look into the code. So first we initialize the count and then we iterate till n is not equal to 0. So at each step we're doing is n in and n minus 1, and then we increment the count. At last we return the count. So here time complexity is O of k, where k is the number of 1 bits, since we have only perform operations for the bits that are 1. The space complexity is O of 1. So here the third approach is using Python's inbuilt function. So it's a very straightforward approach. We are getting the binary representation of the given number using the bin of this number, and then we converting into string, and then we're just counting the number of ones in it, and then that's very straightforward, right? Like we just have a string representation and we just count method of the string. So here the time complexity is O of 1, the space complexity is O of 1. Demo and conclusion. So we have 3 approaches in 3 different methods. So let's try submitting each of them. First approach is accepted. Let's submit second approach. Second approach is also accepted. Let's submit third approach. Third approach is also accepted. So conclusion. Both methods, along with the third approach of using Python's inbuilt function, offer unique insights into the handling bitwise operations. The second approach is also known as Kernighan's algorithm, is more efficient in practice because it directly skips over the 0 bits, reducing the number of iterations required. On the other hand, the first approach provides a straightforward way by checking each bit individually, and the simplicity of the third approach lies in the leveraging Python's inbuilt function to directly count the ones in the binary representation of the number. So mastering these techniques is crucial for tackling the various bit manipulation problems. So while the third approach might seem the simplest, understanding the underlying bitwise operation of the first 2 methods can be incredibly valuable for solving more complex problems where built-in functions might not offer a direct solution. Remember, practice makes perfect, so keep experimenting with different problems to strengthen your understanding and application of bitwise operations. Thank you for tuning into this episode of HackCode. If you found this video helpful, be sure to give it a thumbs up and subscribe to the channel for more coding tutorials and problem solving tips. If you have any questions or suggestions for future topics, feel free to leave them in the comments below. Until next time, happy coding.